Myself, Sourav. I am a PhD student. So today I am going to start the first class of the D and A block elements. And during this class, if you have just some questions, you can ask me. So in this class, before this class, already I have taken the some lectures of the periodic tables. So from that, actually, we can start that from the modern periodic table. So in this modern periodic table, if you say about the D block and this A block element, and also you can the position of the D block and the A block element. Uh, these are actually very important here, where you can see that. Uh, just 1 minute. So this actually D block element. So the positions. First of all, you have to know the positions of the D blocks element. So for the D blocks elements from this group 3 to groups the 12s, and there is period the 4 to this the 6. So the group third to group 12s, these are called the transition element, or these are called the D block elements. And inside this block, there are another group, another block elements are present. This is called the A block elements. So these A blocks elements are started from this lanthanum. Uh, so this is the lanthanide series, and these are the actinide series. So this lanthanide series is started from this that positions, and actinide series is started from these seven groups. So basically, if you see that D blocks is started from the the third groups, and this is the scandium, and there is the three series is present. First one is the 3D metal, this is the 4D metal, and this is the 5D metals. So these three and this four and this five, these are actually coming this n minus one. So n means this is the principal quantum number. So this is the principal quantum numbers. So for fourth periods, whatever D blocks elements are present here, we can say this is the 3D metals element. Whatever the elements are present in the fifth periods, we can say it is the 40 series, and this is the 5D series. So, whatever properties and these atomic radii, we will know about the elements of these three series. This is the 3D, and this is the 4D, and this is the 5D. So, first of all, we will know about. So here we have just mentioned the same things, that D blocks elements, the D orbitals are progressively filled. So now the D blocks elements. So the D blocks, why these elements are called these D blocks? Because we have to know that this element, suppose this scandium, this is a titanium. So scandium, titanium. So these elements, the outer, so this last electrons actually coming to this d orbitals, that's why these elements are called this d blocks element. So d blocks elements means the d orbitals are progressively filled. So group 3 to the 12, these are called the d blocks elements. A blocks element, the same thing, these a orbitals are progressively filled. So there are some issue is that, so there are many the three series of the tungsten metal, like the 3D series, scandium to zinc, 4D series, terbium to cadmium, and this is the 5D series, lanthanum to mercury. So the fourth, this 6D, which begins with this actinides, is the still incomplete. You can see that this is the seventh periods. You can see that. So this is the 3D, 4D, 5D, and this is the 6D. So this is actually the incomplete. So, so the two series of these inner tungsten metals, these are 4Fs and these 5Fs, are known as the lanthanoids, and this is the actinoids. So these are called, so this is the 4F series, and this is the 5F series. So these two series are called, this is the lanthanide series, and this is the actinoid series. And another thing is that d blocks elements means these elements and the last electrons is going to the d orbitals, and d orbitals are progressively filled. If you see this scandium, this is the 3D ones, this is the titanium, this is the 3D two. Uh, Similarly, if you go to this zinc, this is the 3D tens. So progressively, these d orbitals, these whatever electrons, so this is the 21, this is the atomic number, this is the 22, this is the 23, 24, this is the 25. So that when this atomic number is increasing, this last electrons is going to this d orbitals. So similarly, similarly, we can say for this 4D series and this is the 5D series. That's why these elements are called is the d blocks element. So there are some exhibition is there is that the we are saying this the d blocks element. We are saying this the d blocks element means progressively fills the d orbitals. Okay, but here is the comment is that d block elements we can say this type of the element which have the progressively filled or which have this incomplete the incompletely filled d orbitals in its ground state and any excited state. What this means that? This means that suppose if you see this is the zinc, okay. So for that zinc, the electronic configuration is 3D10 4s2. So this is the ground state electronic configuration. So in this ground state electronic configuration, this d orbitals has totally filled up because the d orbitals can have the maximum this 10 electrons. So this the 10 electrons already is there in the ground state. So when it is in the in excited state, suppose the excited state is the zinc plus 2. So for that zinc plus 2, the electronic configurations will be 3D10 and 4s0. So in ground state and also in excited state, the d orbital is totally filled up. But there is the definitions is that for the d block element, this element is have the incompletely d orbital in the ground state or in the excited state. But for the case of the chain in ground state and in the excited state, the d orbitals is totally filled up. So that's why we cannot say that zinc is a transition element. Similarly, for that cadmiums and the mercury are not the transition metal, because if you say this series, there is the zinc, this is the 3D10 electronic configuration, 3D10 4s2. Similarly, for that cadmiums and the mercury, the cadmiums will have the 4D10 and this is the 5s2, and this mercury also will have the 5D10s and this is the 6s2. So these principal numbers will be the increase. So in the ground state and in excited state, this d orbitals is totally filled. That's why these three elements are not treated as a transition element. So here we can say the electronic configuration. So for that d blocks element, whatever transition metal is present, for that case, the general electronic configuration is n minus 1, d2 10, and ns2. Here n equal to the principal quantum number. So for the 3D series, the n equal to will be the force, and this 4D series, the n equal to will be the 5, and this is the 5D series, n equal will be the 6. So in this way, you have to calculate the electronic configurations of the transition metal. And there is another comment is that half and completely filled the state of these orbitals are relatively the more stable. And a consequence of this factor is reflected in the electronic configuration for this chromium case, and this is a copper case in the 3D series. So consider the case of the chromium, the electronic configurations will be the 3D5 4s1 instead of the 3D4 4s2. What is the reasons for that? So for that, if you see the outer electronic configurations of this transition element, there is some issue, there is some important points in the transition state when we are going to draw the electronic configurations of the 3D series. Then there is a rule is that when we are coming, when there is a chance to fill the half field and this the full field the orbitals, then that actually configurations will be preferred than the others because this upfield electronic configurations and this full-field electronic configurations are the stable. Now the question is that why this upfield and this is the full-field electronic configurations are the stable? Because if you uh, because there is reason because if you see the electronic configurations in the coordination chemistry chapter, there is the tetrahedral, there is the octahedral geometry. Okay, so the five when we are going to this 3D orbitals. Okay, so there is the four and there is the five 3D orbitals. So when but in presence of ligand in coordination chapter, there is the crystal field splitting is happened. uh, so this is the crystal splitting of that octahedral geometry. Okay. So for that octahedral geometry, if you arrange this five electrons, okay, so in this way you have to arrange. So one, two, three, and this is a four, and this five. So if you say this, when we are announcing these five unpaired electrons in these 5D orbitals in this octahedral geometry, then there is a symmetry. Okay, you can pass a line where the two electrons are both are the actually in position, but both are the mirror image. So there is a symmetry. In case of if you see this octahedral geometry also, so this is the octahedral crystal splitting. Here also you can arrange this electron, this five electron, you can arrange in this array. And there is also a symmetry is present. Okay, so this is for this half filled tetrahedral geometry. But in case of full field, in case of full field, suppose this is the full field, that means this there is the D10, there is the 10 electron is present. So you can arrange in this array 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this case also, there is the symmetry is line. So in case of the half field case and in case of the full field, so there is symmetry is coming in the electronic configuration. That's why this actually configuration, the half field and full field configuration are the more stable than this other. Suppose I am talking about the D7 electronic configuration. This is the octahedral. So when it is a D7, so 1, 2, 3, 5, 4, 6, 7. So here there is no symmetry. So this actually in not stable, not more stable than this half field and the full field. That's why when is this symmetry, when this half field and the full field, this type of the situations will come that will be more favored than these others. So that's why when we are coming to this chromium, so it has the atomic number 24. So there is two possibility of electronic configuration in general. This is the 3D4, 4s1. Another configuration is 3D5, 4s2, and this is another configuration is 3D5, 4s1. So here it is the not half field, but this is the half field. So it will be the favor. That's why the, for that chromium case, it is going to the electronic configuration 3D5 4s1. In case of the manganese, this is the 3D5 4s1. Iron also same. But in case of the copper, this electronic configuration is the 29. So similarly, we can arrange in this array 3D9 4s2, but the electronic configuration will be 3D10 4s1 because it is a full field. That's why these are the two exceptions where the favoring the half field and the full field. Another, there is a some trick to remember the electronic configuration in this array. You just remember the atomic number 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So how we will remember this atomic number? So this is the 21. So when this the 21, you arrange this is one. So 3D 1, 4 is 2. Similarly here also 3D 2, 4 is 2. Here also 3D3 4s2. So in this array, so this is a 3D6 4s2, or this cobalt 3D7 4s2. So this all the electronic configuration in the ground state. Similarly, you can so this is for the 3D series, this is for the 4D series, and this is for the 5D series. So just you change the principal quantum number for that 4D series and the 5D series. You can easily remember the electronic configuration. And there are the some exceptions for that chromium case, molybdenum case, tungsten, or similarly copper and the silver and the gold. So these are the some important points regarding this electronic configuration you have to remember. There are the some physical properties we will know now. Some physical properties is that is the 3D or the transition metals are the very hard, and it has the law of uh, one polarity and the strong metallic bond. So they form the strong metallic bond. And so why this form they form the strong metallic bond? There is some reasons, there is some exceptions. This is a very important point. And another point is that involvement of the greater number of electrons from the n minus 1d in addition to the ns electrons in the interatomic metallic bonds, and this is the stronger interatomic bonding. So these are the some important points, some physical properties for the d orbital elements. So first of all, I will talk about this actually points. It's a very important thing. This the involvement of the greater number of the electrons from n minus 1d in addition to the ns. Because if you see the general electronic configuration in n minus 1d, this is the 1 to 10s, and n is 1 to 2. So this is the actually general electronic configuration. So these are actually valence electronic configuration, we can also say, because the valence electrons are entering this the d orbitals and this 4s orbital. So this is the valence orbitals also. So these orbitals actually are going to participate when they are forming some metallic bond. So here the n minus d orbitals. So d orbitals electrons actually more the participating when the d orbitals electrons are more participating in forming this metallic bond, then they have the some strong metallic bond. So if you see for that series, so when the strong metallic bond will have, then the melting points will be the high. The strong metallic bond means the melting point of this atom will be of this element will be the high. So if you can see, this is for the 3D series. So the titanium, this is the for the titanium melting point. Okay, when we are going to this titanium to vanadium, then the chromium, then the melting point is increasing. Because if you say this scandium titanium, so titanium is 22, scandium titanium, vanadium is 23, chromium is 24. So this is the 3D2 4s2, this is the 3D3 4s2, and this is the 3D4 4s2. So what we are saying that the involvement of the greater number of electrons. So when we are going to this titanium to the vanadium, vanadium to the chromium, then this number of electrons in the d orbital is increasing. So when in these orbitals the number of electrons is increasing, then this number of electrons are also are participating in forming the metallic bond. So for that case, the chromium, the metallic bond will be the more strong. That's why the chromium has sorry. So this electronic configuration will be the 3D5 4s1. So this is a 3D5 4s1. So the chromium will have 24, 23. So the chromium has the greater the melting point than the other titanium, vanadium, and the chromium. But in case of the manganese, the drop graph. In case of the manganese, if you see the melting point is the drop, because on this manganese case, if you see the electronic configuration is 3D5 4s2. What is that? Because if you see for that chromium case, there is a 3d5 forest 1. So one unpaired electrons also is present in the forest orbitals, and also five unpaired electrons is present. But in this case, this for this chromium, this one unpaired electrons actually going to this forming this bond. But for this manganese case, this is the 35 forest 2. 35, that means it is a it is a half filled d orbital, it is a more stable, and for that case the forest 2, it is the paired up. So there are the not this type of the strong metallic bond for this manganese. That's why this melting point is decreasing than from this chromium. Again, it is the increasing for this iron, cobalt, nickel. And then in case of the copper, also it is the decreasing, because the copper, if you see, this is the electronic configuration is written in the forest one. So when it is the coming this half filled and the full filled electronic configuration, then the then the metallic bond is going to the weak, and this melting point is the decreasing. So there are the same things, same points. Here the mention the melting points of this metal rise to a maximum D5, except for this anomalous value of this manganese and the rancium, and for the regularly as the atomic number increases. When it is at atomic number increases, this is also increasing, and trends for the melting points of the 3D metals, 4D, and this 5D transition metals. So there is another point. The strength of the interatomic bond in transition element is roughly related to the number of the half-filled orbitals. In the beginning, the number of the half-filled orbitals increase till the middle of the period that causes the increase in the strength of the interparticipate bond. But thereafter, the pairing of this electron in the d orbitals they occur, and no the half-filled orbital decreases. So another point is that there is another point when we are going to this iron, cobalt, and nickel, these have also the melting point is lower than the scandium and titanium and vanadium, because when we are going to this iron case and cobalt case and nickel case, so for this iron, it is the 3d6 for S2, 3d6. This is the 3d7, and this is the 3d8. So when we are talking about this 3d6, that means there is unpaired. The number of unpaired electrons is 1, 2, 3, 4, 5, 6. So the unpaired electron is the 4. So here the unpaired electron will be the 3. Here the unpaired electrons will be the 2. So number of the unpaired electrons also the decreasing. When this number of unpaired electrons will be the decreasing, then the metallic bonds will be the weak. So then the melting point also the decreasing. That's why the when we are going to this iron to cobalt, cobalt to nickel, then this value also the decreasing. But for that case of the titanium and the vanadium, there is the lots of the number of unpaired electrons. Whatever electrons is present in the d orbitals, these electrons are the unpaired. So that's why for that case, actually, the metallic bond is more stronger and melting point is higher. So these are actually point. Here it is written. Another physical properties is that enthalpies of the atomization. What is called this enthalpies of the atomization? So for that case, what is happening here? Enthalpies of atomization means some amount of the energy is needed to form this atom from a from a molecule. What is that? Enthalpies of atomization, it is defined as delta H0. So this is the change in the enthalpy when one mole of bonds are completely broken to obtain the atoms in the gas phase. For example, the atomizations of the methane molecules. So atomizations of methane, if you see, methane has the 5 atoms. Okay, so there is the 5 atoms in the gaseous state. So these 5 atoms, this is actually forming a tetrahedral bond. So it is a molecule. So here this carbon hydrogen bond is present. But when we are doing this atomization, then this carbon element is separated, and 4 hydrogens also are separated. So that means we are here the broken the 4 the carbon hydrogen covalent bond. So to break this for the CH bond, this amount of the energy is needed. So this is called the enthalpy of the atomization. So this amount of energy, this amount per mole, 1665.0 kilojoule enthalpy is needed to break this 4CH bond to form this atom from this methane or for the atomization of the methane. It is called the enthalpy of atomization. So similarly, we can say for that any diatomic molecules like the hydrogens. So hydrogens means the H2 gas means there is the two hydrogens. They are the forming this sigma bond with this S orbital. So for the diatomic molecule, the enthalpy of atomization is equal to the enthalpy of the bond dissociation. Because for the diatomic molecules, there is the one bond is only present. So to break this bond, we will get these hydrogen atoms. So that's why for this diatomic molecule, it is the equal to the enthalpy of the only one bond dissociation. So for that H2, the atomization is very less compared to this methane because there is the four CH bond are present, but here only the HH1 HH is the covalent bond. That's why it is the very less for these hydrogen atoms. For that atomization, it is the value is the 435 kilos per mole. So it is called the enthalpies of the atomization. So with this concept, concept, when with this concept, this enthalpy of the atomization, this concept will come to this 3D series and the 4D series and the 5D series. Then we have to think about that for which series have the more stronger metallic bond. So when the strong uh, metallic bond is present, metallic bond is present, then that will have the higher value of enthalpy atomization. That means the delta is zero value. Because to break this strong metallic bond is needed the higher amount of this delta is zero. So now, again, this strong metallic bond, when it will be formed, that will have the number of the valence electrons. Uh, when so, if you consider this 3D series, 4D series, 5D series, we know that 5D series has the higher the valence electrons, and 4D is the less, then 3D is the less. That's why the 3D elements have the less actually enthalpy of the atomization value compared to the 4D series compared to the 5D series. So these are the car you can see for this is for the 3D, this is for the 4D series, and this is for the 5D series. Because all actually depends on the strong metallic bond. Because the enthalpy of atomizations means the bond dissociations. So greater number of valence electrons, stronger the interatomic attraction. That means the stronger metallic bond. So here's the stronger bonding between this atom, resulting in the higher enthalpies of the atomization. This is the simple thing. All are the points that the core the related to each other. Okay, so this actually we can relate these enthalpies of atomizations with the 3D series, 4D series, and the 5D series. These are the very interesting and the physical properties. The most very important is the physical properties is the atomics and this ionic radii of the transition metals is the diplox element. So here, if you see the first the series, okay, first the curve, we can see that uh, for we so this is for the 3D, okay, this is for the 4D series, and this is for the 5D series, okay. So for that scandium, as the metallic radius is 160 around this 160 pm picometer. Then when we are going to this scandium to titanium, then this atomic radius value is decreasing. In this titanium to vanadium is also decreasing. Vanadium to chromium is it is decreasing. Then for this manganese, it is somewhere, it is some value is increasing, then again the decreasing, then the decreasing, then the increasing, then the value is also the increasing. So in this case, so from that curve, we can say that first the atomic radius value is decreasing in the middle of the series of the D block, at the 3D series. This is the first, this is the decreasing. Then it is the same. There is a some value either from this manganese to nickel. If you see, this value is more close to each other, to the same. Then when we are going to this copper and the zinc, this atomic radius value is again the increasing. So there is the anomalous change of this atomic radius value. But the question is that the same strength, yes, same the strength actually is it is following for that 4D series also. It is following all that the 5D series also. But the question is that why this type of this environment is creating in the atomic radius or the metallic radius as value. First, it is decreasing, then it is the very, very the close value for that manganese to nickel, then the again the increasing. So to know that the regions of this uh, event, we have to know the shielding effect. So this is the there is the some two important points, some two important factor is that the electronic attractions between the positive nucleus and the electrons and this mutual repulsion of this electron. What is that? So if you consider here, it is a nucleus. So suppose I am talking about this 3D metal, any 3D metal, suppose it is the manganese. Okay. So for that manganese case, if you say, suppose, okay, no, so there is the two electrons. So suppose this is the 3D and uh, and this is the also the suppose this the forest. Okay. So let's so this is for this 3D element. If you consider this the nucleus, any element, then so it is a nucleus, and there is the two orbitals are the present. Okay. So first orbitals have the two electrons. There is the two electrons, and this is the valence orbitals or the outer shell orbitals. There is the another the electron is present. So when we are talking about the electrostatic attraction means there is attraction between the positive charge and the negative charge. Now this nucleus is the positively charged and the electrons are the always the negatively charged. So the attractions will have the positive charge and the negative charge. So here the attractions will have the between the nucleus and the electron. So there are also the attractions between these electrons and this nucleus, and another attraction is this nuclear between this nucleus and this electrons. So these are the attraction. So this is the first point is that attraction even. Another point is the repulsion. When we are talking about this repulsion, that means that the repulsion between the positive repulsion and the another repulsion is the negative negative. That means this between the two electrons. Okay, there is a negative repulsion. So here the repulsion is present between these two electrons. There is a two electrons that present. So between these two electrons, there will have the some repulsion, and there is the attraction. So these two factor actually present in every elements. Somewhere for the some elements, this attraction value is increasing, the repulsion is decreasing. Some for the some element, this attraction value is decreasing, this repulsion value is increasing. So what will be happen? Or this when the attraction is increasing, the repulsion is decreasing. When this repulsion is decreasing or the attraction is increasing, what will be happen? So these two factor actually more important for this 3D series and the for that atomic radii and these are the ionic radii of that transition metal element. So to know how this factor actually working in this case. So for that case, here I will discuss what is actually happening here. Suppose this is the nucleus. Suppose here this is the for that copper case. So this is the copper and the potassium. Before that, if you talk about this titanium, vanadium, chromium, manganese. So first that actually series, first I will talk about that. So this is the 21, 22, 23, 24, and this is the 25. Okay. So for the scandium, so this is the nucleus. Okay, so this is the nucleus, and this is the two orbitals are the present. Suppose so the electronic configuration is 3D1. This is the 4s2. So what will be happened here? So this is the 3D, this is the 3D orbitals, and this is the 4s orbitals. So for that every element, if you see for that every element, 4s orbitals are uh, so for the scandium case, for the scandium case, so there is the two electrons here the present. So there is a two electrons are present, and there is the one electron is present. So this is the attractions will be have here. For that scandium's case, there is the attractions between this nucleus and this electron. So this is for the scandium. But when we are talking about this titanium, so the another electrons also is present here. So then again, these attractions will be here. So when the attractions will be increasing between these electrons and this nucleus, then these valence orbitals electrons will be more closer to this nucleus, then the size will be the decreasing. So when this attraction, when this attraction is increasing between this nucleus and these electrons, then these electrons will have more closer to this nucleus, then the size will be the decreasing. So that's why when we are going to this scandium to titanium to vanadium, so when we are going to this vanadium, then another electrons in increasing. So there is the three electrons is present. Okay. So more attractions will be happen between this nucleus and these three electrons. So these orbitals, these electrons will be the more closer than this scandium and the titanium. That's why when we are going to this scandium to titanium to vanadium, then this atomic radius to metallic radius value is decreasing. If you see this trend, when we are going to scandium to titanium, titanium to vanadium, even we are going to this vanadium to chromium. Okay, when we are going to this chromium, then this is a 3D5. Oh, this is a 3D5. Then the five electrons is present in these d orbitals. So more attractions will be happened here. But when we are going to this manganese, then we are going to this iron case. So when we are going to this manganese, this iron, cobalt, and this nickel, what is happening here? They are actually what is happening. So this is the nucleus, and this is the 3D orbital, and this is the 4 orbital, 4s orbital. So when we are the talking about this manganese, this is the 3D5, and this is the 3D6, and this is the 3D7, and this is the 3D8. So from this manganese to iron, iron to cobalt, cobalt to nickel, again this number of electrons is present. So when this number of electrons is increasing here in this d orbitals, this another factors will come here. This is the repulsion. Okay. So there is attraction also is there. Attraction also is there between this nucleus and the electrons. Another factor is the repulsion also is there. Electron to electrons. This repulsion also is there. So attraction repulsions both are present for this manganese to nickel. That's why two factors are opposite to each other. So they are the cancel to each other. That's why the atomic radius is the same for this manganese to iron to cobalt and this nickel. When we are going to this copper case and when we are going to this zinc case, again this repulsion is a more high. When we are going to this copper case, it is the 3D10 system. Uh, when we are going to this zinc case, it is the 3D10 system. So here, the repulsion factor is more promoting than this attraction factor. That's why this atomic radius value is increasing for that copper and for that zinc case. So there is the two factor. One is the repulsion, another is the attraction. So, dependent on these two factors, this strength actually is following. So, here I can write that the scandium to chromium. Here the attraction factor is more permitting. It is the and for this manganese to nickel, there is the attraction factors is equal to the repulsion factor. Okay, but for this copper and the zinc, there is the only repulsion factor is present. That's why that's why this value for that copper to zinc, this atomic radius is increasing than the other case. So with this topic, I will now talk about lengthenite contraction. It is the very interesting for that d orbitals. So when we are talking about this lengthenite contraction, because if you see this periodic table, the lengthenite series, this 4F actually, this lengthenite is started for this lengthenite. Okay, here is lengthenite contraction is happened. But what is the lengthenite contractions? So to know that the atomic size, when this atomic size or this ionic area of this tripositive lanthanide ions that decrease steadily from this lanthanum to lutetium. When we are going to this lanthanum to lutetium, then this atomic radius value is still decreasing. Uh, is still decreasing. Uh, but why? The question is the why. Because the increasing the nuclear charge and the electrons entering in this n minus 2 f orbitals. What is the reason? What is the fact is that this is a very, very important here for this lanthanide contraction, because you see this lanthanum to lutetium, there is 4f orbitals is start. At least 4f orbitals start. That means that there is number of the valence electrons. This valence electrons is this last electrons is going to this f orbitals. Okay. The another point is this gradual decrease in the size with this increasing the atomic number is called the lanthanide contraction. Okay. So the lanthanide contraction is the result of a poor shielding of the 4f electrons. So what is happened here? If you so here you can see that when we are going to this lanthanum to rhodesium, this atomic radius value is still decreasing, but this atomic number is increasing, but this ionic radius is the decreasing. Okay, so this is the strain. So now the question is if why actually this type of the lanthanide contraction is happened. In this slide, I will discuss. So here you can see that. So this is the nucleus, and this is the 4f orbital. This is the 6s, and this is the 5d. So 5d is the outer shell, 4s, then the this is the 6s, and then the 4f orbital. 4f is the inner shell. Now the size actually depend on the here. The size actually depend between the attractions between. Suppose this is the one electron and this is the nucleus. So the size actually depends the attraction between these electrons and this nucleus. How much the attraction is present? When this attraction is present, more, then these electrons will be more closer to this nucleus, then the size will be decreased. Now the question is, we are talking about this lanthanide contraction. Here it is the mention that this gradual decrease in the size with an increasing atomic number. When we are atomic number is increasing, then the ionic radius value is gradually decreasing. That means this attraction value, this attractions between these electrons and this nucleus is increasing. That's why this atomic radius is decreasing. But the question is that why this attraction is increasing? First of all, why this attraction is increasing? Because we know that this order of the shielding effect, the shielding effect, uh, the shielding effect order, we know that s orbital has the most shielding effect, then the p orbital, then the d orbital, and then the f orbitals. So the f orbital has the less shielding effect compared to the sp and the d orbitals. Now this f orbital is present here, uh, between this IB6X and this nucleus. Okay, so the f orbital is more closer than the IB and the 6X to this nucleus. Now the question is that, again the question is that, there when this f orbital is present, suppose there is a three electrons is present here, so there is the pore shielding effect. So due to this pore shielding effect, that means that this orbital cannot shield this electron, this outer shell electrons, uh, the nuclear charge effect, from this nuclear charge effect of this nucleus to this electron, this outer shell electrons. That is called actually pore shielding. So due to this pore shielding, the attractions will be the higher than this other. Now the when this atomic number is increasing, when this atomic number is increasing, suppose there is the three electrons is present. There is a three electrons is present. Now there are four electrons and this is the five electrons. The number of atomic number is increasing. That means the number of electrons also will be increasing in this f orbitals. So when this electron will be the increasing, then that will be the more closer. So that is actually written here. So nuclear charge of the f orbital is the more. First of all, first region is the nuclear charge of this f orbital is the more. That means this f orbital is more closer to the nucleus. Another point is that due to the unsymmetrical shape of the f orbital, it cannot just shield the outer orbitals, because the f orbitals, whatever shape is present, it is actually unsymmetrical. That's why it cannot just shield the outer orbitals, so that the outer orbitals also that feel the nuclear charge. Another point is that nuclear force, nuclear force of the attraction on the outer shell electrons increases. Therefore, it inverts towards the nucleus and causes the reduce in the size. So, due to this F orbitals, this atomic size is actually and then the atomic size of this F orbitals in the lanthanide case, it is actually decreasing. That is called the lanthanide contraction. So, because of actually the reason is that because of the F orbital, force shielding effect of this F orbital. Now the question is that why this F orbital has the force shielded, because it has the unsymmetrical shape, and it is actually the nuclear charge of f orbital is the more than the s orbital and the d orbital. So here I will stop the class, and another in this class I will discuss about this. Another question is that in the series of this Scandia, just 1 minute. In the series of this scandium to when we are going to this zinc, okay, 21 to the 30, the enthalpy of the atomization of the zinc is the very, very lowest. This is the 126 kilojoule per mole. But question is the why? Why it is actually very, very less? Similar, the reason already I have told in this class, that the enthalpy of the atomization, it is actually the required of the amount of the energy is required to break this bond. So now this bond, this metallic bond, when this the metallic bond, this metallic bond is the more stronger. When it is the more stronger, then the atomization's value will be the high. Now the question is that when it will be the more stronger. So the metallic bond is the more stronger. That means that this orbital, these electrons, the number of unpaired, this number of the unpaired electrons is the higher number of the unpaired electrons is present in this d block elements. Now, whatever element is present, which elements has the number of unpaired electrons is the more high, or that case actually metallic bond will be the more stronger, or that case of the enthalpy of the atomizations value will be the higher. But here, if you see, for that the zinc, the electronic configurations, for that the zinc, the 30. So the electronic configurations will be the 3d10, and this is the 4s2. So the 3d10 4s2, that means when we will draw the electronic configuration in this array, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is the 4s2. So this is the 3d10, and this is the 4s2. So there is the no unpaired electrons is present. Okay, there is the no unpaired electron, because if you say, so this is the suppose zinc. Okay, So with this zinc, the another elements will form the some bonds. So to form this bond, it will have the unpaired electrons. When this unpaired electrons will be the present, then this type of the bonds will be the more stronger. So for that the zinc case, there is the no unpaired electrons. That's why if whatever bonds will be the formed with this another element, this type of the metallic bonds will be the very weak. So to break this weak the bond, the enthalpy of the atomization sparrow will be the very less. So this is the actually reason for the gene case has the lowest atomization value. So in this class, what I have taught that first of all, the D block element and this A block element, the positions, and I have taught about the physical properties of melting points and the enthalpy of atomization and this atomic radii. Another is the lanthanide contraction. So I will stop. If you have any questions, you can ask me from now. Thank you.